What's up, guys? This video we are going to talk about Taylor theorem on the remainder. Right? Suppose we have an infinitely differentiable function like this. Then we know that so this is differentiable. Suppose this is differentiable anywhere on the real line. So then we can find the Taylor expansion as around at any point, say A. So suppose we found the Taylor expansion of f around A, so it is, which is a infinite series. We know that this infinite power series converges to f of x over x over this interval here. So here r is the radius of convergence of this power series. You can find by using a ratio test. So r can be found, then over this interval this power series converges to f of x. So let's see if you consider a part of this polynomial, part of this uh, series, that means a polynomial. So we cut down this infinite series from somewhere here, then we get a polynomial. So the highest order of that polynomial is n. Here this is the highest exponent, so x to the power 1, x to the power 0, x to the power 1 up to x minus a to the power n. This is a power series. This is a polynomial in x minus a. The degree of that polynomial is n, the highest exponent, right? So n, this is called nth degree Taylor polynomial. So we are going to approximate function f of x by using this polynomial. So definitely you know that at the center center A, the function and this polynomial coincide. When you plug a into the right hand side of this one, so this becomes 0, these things become 0, so you end up with having f of a, then f of a coincides with if both are the same, right? These are the same. So at the center, both the approximation function and the function value at that point are the same, right? So there is no difference, right? If you go away from the center here, so if you go away from the center, you can see an error between these two. This is the actual function, this is the approximation to that function. So you can see an error between these two, some gap between these two functions, the actual function and the approximation to that function, right? So let's denote that error, the gap between those two functions is r of x, right? So now we are going to investigate this error bound, right? So we want to measure this error. So how does it vary when you go away from the center? So we need to get an idea about this error bound. So we can say, if you so definitely you know this is the approximation to f of x. We can say this has, so suppose, so you found, let's say, wait a second, for instance, we are going to find a bound on the error for when e to the 0.5 is approximated by the fourth order Taylor polynomial of e to the x centered at 0. So definitely you know the Taylor expansion, the Taylor infinite Taylor expansion is this. Now we cut down this Taylor expansion from here, then we get the fourth order Taylor polynomial. So now we use this fourth order Taylor polynomial to approximate this function. So when you approximate this function using this, you know that there is an error. So at the center, so this is your right hand side. At the center, so this is t sub 4. This is the fourth order polynomial. So you cut down from here, then you get this one. You cut down of your Taylor expansion, infinite Taylor expansion from here, then you get the fourth order Taylor polynomial. So you use this approximate function to evaluate value of e to the x. So at the center is 0 here. This is the center. At the center, so you can say, so here left hand side, what is the value of left hand side? E to the 0, which is 1. So if you plug the center value into the polynomial, you get the same value here, 1, right? 0, 0, 0, 0 here. So you get the same one. At the center, so there is no difference between the approximation function and the actual function. But if you go away from the center, so it will generate an error. So we try to identify that error bound over some close interval. Let's find that. So we know that from the Taylor theorem that Lagrange, this is called Lagrange remainder. So this remainder is bounded by this value here. So this value over a close interval here, right? So in the problem, if you go to the problem again, if you go back to the problem again, so we want to approximate e to the 0.5 by using this fourth order Taylor polynomial, right? Fourth order Taylor polynomial. So from this theorem says that Lagrange remainder is less than or equal to this one here, a mod of f to the power. So here f fifth order fifth derivative of exponential function times x modulus of x minus c. The center in this case is 0, the x minus 0 to the power 4 plus 1, because we are approximating exponential function by using fourth order Taylor polynomial, right? I hope this makes sense to you, right? This one. So here c is a value between 0 and x generally. So but here we want to find the error bound at 0.5, right? So in this case, your 0 in between 0 and 0.5, right? So let's go back to the function. So we need to find the fifth derivative of this. We know when you differentiate exponential function many times, you get the same function, right? So and also we know that exponential function is an increasing right? Exponential function is increasing, then the maximum value occurs. So if you consider this close interval here containing this point, right? Right? So the maximum value of that function exponential ex occurs at here, right? Then so this modulus of the fifth derivative is less than or equal to this number, then you can put that number here. So then at point 0.05, at point 5, the error bound is less than or equal to e to that number times. So plug numbers into here. So this time we consider 0.5, that means 1/2. So 1/2 to the power 5 over, so what do you, factorial 5. This should be factorial 5. Yeah, factorial 5, right? Factorial 5. So when you calculate this number, you will get something like, I think you will get something like this 0.0004. So we can say that, so the error bounds, if we move away from the center, if you move away from the center to this point, so if you approximate exponential function from the fourth order Taylor polynomial, you get this much error bound. You get this much error bound. So in the problem, give a error bound on the error for when e to the 0.5 is approximated by the fourth order Taylor polynomial of exponential function centered at 0, right? I hope this makes sense to you. This makes very sense to you, right? So if you move away from the center to this point, so you can say that the approximation value computed from the fourth order polynomial has an error. That error does not go beyond this bound. That's the main idea. So we can say it has an error, but it does not go beyond this number, right? Okay, I hope this more sense to you, right? This makes more sense to you, right? I hope you understood this one very clearly. So in my next video, let's compute the, so next video I'm going to discuss the following, right? So now suppose we are given the error bound. Now we want to find the number of terms we should, so we want to identify the order of the Taylor polynomial, the right order of the Taylor polynomial, so that, so you know that we approximate some function using the Taylor polynomial, right? So this time you are given the error bound. So then we are asked to find the order of the Taylor polynomial. So when you approximate some function using that Taylor polynomial, so you are asked to find the order of Taylor polynomial. The error bound generated from this Taylor polynomial when you approximate some function, right? The error generated from this Taylor polynomial should not go beyond this form. So we have to identify the order when you are given the error bound, right? Let's do it in my next video.